Hello again. So today we're going to look at sampling distributions with means. So numerical data, how do we deal with the sampling distribution and find those probabilities from a normal model if we're dealing with means. So we're going to go straight into an example and then talk about how it looks a little bit different for means than for proportions. So example 1 says that the manufacturer of a certain brand of aluminum foil claims that the amount of foil on each roll follows a normal distribution with a mean of 250 square feet and a standard deviation of 2 square feet. So this first question says, what is the probability that one randomly selected roll of foil has an area of less than 248.5 square feet? So this was just asking about one. We're not even talking about a sample or a sample mean. And remember, a sampling distribution is looking at a sample statistic compared to what we would expect for samples of that size. This is just talking about one. So this is actually what we originally learned with normal model. We would just do that same thing. So we're just finding the probability that a single value x is less than 248.5 square feet. I have my normal model because they told us that this distribution is normal. My mean is 250, standard deviation is 2, so I could add and subtract standard deviations either direction. I would find a z-score. So z-score is equal to our observed value of 248.5 minus the mean of 250 divided by 2, which is negative 0.75. So about right here, not quite a full standard deviation below the mean. And then we want less than that, so I'm shading to the left. And then I would go to my z-table and look up that z-score. My z-table gives me the less than area, so I could just keep it like that. And I would get a area or probability of 0.2266. So that's just regular normal model z-score stuff that we've done in the past because we're just talking about one. Where it would be different is if I said, what's the probability that a random sample of 10 rolls of foil has a mean area? So the difference between that last question and this one is that A was just talking about one single roll, and this one's talking about a sample mean for a sample of size 10. That's where there's a difference between just an original population distribution and a sampling distribution. So it's good to look for those words. Sample mean, right, is dealing with the sampling distribution. So we're actually going to skip this question for now. I'm going to go through this one in class, but I want to get to my other example. So this one we'll kind of do as an example in class next time and go through how to do that one just for extra practice. So let's review ourselves again. A sampling distribution is a collection of a large number of sample statistics, either means or proportions, of a given sample size. And again, sampling distributions are useful because they give us an idea of what to expect for a sample from a population, helps us determine whether a sample statistic is higher or lower than what we would expect. So because we're talking about different types of data, we're talking about numerical and means, I want to do a different little kind of applet to show you what's going on with means. So here is an applet where I have a collection of data. So this is a collection of numerical data of how much people sleep. So we have all this collection of data. What I'm going to have it do is I am going to this right here is the population distribution right here. So it's telling us for the whole population, what is the mean and the standard deviation, and kind of we can see that the shape is roughly normal. So what I'm going to do is I'm going to have it take samples of size 10 many times, and I'm going to slowly start building this sampling distribution. So if I just took one sample, there's my sample right here, and then there was the sample mean. And if I keep doing that, right, so there's my second sample, there's my new sample mean. There's my third sample and my third sample mean. And I could keep doing this for a while until I take a whole bunch of samples. And just to make this a little bit faster, I'm going to say take 100 samples of size 10 and find the means of each of those samples. And now we can kind of see that sampling distribution. Now it's kind of hard to tell because, and if actually I'm going to change the scale to be the same scale as the population just so you can see that visually. So the scale on the x-axis is the same as it is for the population. So I can see for this that the spread is much smaller. The standard deviation of our population was 1.5. the standard deviation of our sampling distribution is 0.4, right? So we can see that the spread got much smaller, but my mean stayed about the same. So 8, and now it's 8.03, right? And I can kind of see if I wanted to, I'm going to reset this and say, what if I take bigger samples? What if I take samples of size 30? And I can see that my sampling distribution is even smaller. The standard deviation is even smaller than it was before because my sample size got bigger, but my mean is about the same as the population. But now we want to look at what if we have one that is not symmetric or unimodal to start with. So I'm going to do a new distribution, and this one you can see is skewed to the right. Skewed to the right. So I'm going to go ahead and do the same thing I did before. I'll start with samples of size 10, and I'll draw samples. So I did 100 samples of size 10, and there's my graph. And you may notice, again, it's kind of hard to tell, and I'm going to go ahead and rescale it so it's a little bit easier to see. You'll notice that that distribution is still a bit skewed to the right. It's a little bit more normal than my population, but it's still a bit skewed to the right compared to the population. So even though I took samples and found sample means, my distribution isn't quite normal yet. But if I take samples of size, let's say 30, right, my distribution still looks a little skewed to the right. If I rescale it, I can kind of see that it's much closer to what we would call normal. If I take samples of size 50, right, I can see it's even a little bit more normal, kind of looks a little bit skewed to the right. But the bigger my sample is, or my sample size, the more normal that sampling distribution is going to look. And of course, the same thing happened that we talked about before, where the mean stays about the same as what it was for the population, and my standard deviation gets smaller as sample size gets bigger. So there's a lot of things going on there, and I want to kind of put some context to it. So population distribution, let's say we start off with a population distribution that is uniform. If I take many samples of this size, the sampling distribution will look something like this if my sample size is 2, and it'll look like this if my sample size is 25. So notice that my sample size of 2 still doesn't really look what we would call normal, but by the time I have a big enough sample size, that distribution looks roughly normal. If my population is skewed to the right, sample sizes of 2 might look like this, still a little bit skewed to the right, but a sample size of 25 is going to by that time look roughly normal, right? And then of course, if I start off normal, my sampling distribution for size 2 is still going to look normal, but it's just a little bit thinner. And my sample of size 25 is obviously going to look normal, but much thinner. So here's what I want you to take from that, some rules we have. This is called the central limit theorem. The central limit theorem tells us what happens to the center and the spread and the shape of sampling distributions for means. And it says that when the sample size is large enough, the distribution of sample means, that sampling distribution, is roughly normal even if the population was not. So large enough sample size, typically around 30-ish. A lot of times 25 to 30 is a big enough sample size. Really kind of depends on what the original population shape was, but give or take 30. And then this is our, from our formula chart, can't talk, the mean of that sampling distribution is just going to be the mean of the original population. The standard deviation of that sampling distribution is going to be given as the original standard deviation of the population divided by square root of n. Again, they're on your formula chart. And of course, if we want to know the shape of the distribution, we have to check some conditions and assumptions, just like we did for proportions. And the central limit theorem is going to help us with that. So let's look through our assumptions and conditions for means. The first one is the same as with proportions. We need to check that we have a random sample so that we're avoiding bias. Remember, bias affects the center of that distribution. The second condition is that 10% checks for independence between trials. So we want our sample size to be less than 10% of our population. This is just making sure that our data is accurate. It also helps to make sure that the standard deviation formula will work correctly. And then we have to check for, is the sampling distribution roughly normal? And for means problems, there's actually 2 ways that we can check this. The first way is if our population distribution was normal, if they told us in the problem that the population distribution is normal, then we know that any sampling distribution that comes from that is also going to be normal, no matter what the sample size is. Right? But if our population distribution was not normal, or if it's unknown, then if our sample size is bigger than about 30, 25 to 30, we know our sampling distribution will be roughly normal, even though the population wasn't normal. So that third condition for normality, you're checking for were we given that the population was normal, or is our sample size bigger than 30, or both, but one or the other will suffice. So we'll look at what this looks like in an example right now. I want to remind you of our basic steps for solving sampling distributions problems. We want to check our conditions, find the mean and standard deviation of the sampling distribution, use the normal model to find a probability, and then interpret the probability. So let's look at this example. So example 2, movies in 2019. The number of movies viewed during 2019 by students at a large high school has a mean of 19.3 with a standard deviation of 15.8. However, the distribution of numbers of movies watched is very skewed to the right. So that is the population distribution. They're telling you that the population number of movies watched in 2019 is skewed to the right. So A says, if we wish to find the probability that one randomly selected student watched fewer than 12 movies in 2019, can we calculate that probability using the normal model? So the answer is no, we can't. Because one student is not a sampling distribution. One student, we would be using the population distribution. And I can't use a z-table or a normal model for a distribution that is not normal. So this would not work with one student because one student is going with the population distribution, which they've already told us is skewed. So I would not be able to calculate this probability. What if we take one sample of 80 students? What would the shape of that one sample of 80 students' numbers of TV or movies watched look like? Now, you might be tempted to say that that would be normal because 80 is bigger than 30. It's a big enough sample size to make the distribution roughly normal. And that is true for a sampling distribution. However, this is not actually a sampling distribution. This is just one sample of 80 students and those 80 students' numbers. We didn't ever say anything about a mean, and a sampling distribution, remember, is a collection of sample means. So this one is just talking about a sample of students' original values. Let me show you a little bit more about what I mean. So let's say this is our parent population. It's skewed to the right, as the problem we're dealing with says. One sample means that I'm randomly picking 80 values from this parent population and putting those values on a graph. That graph is going to start to mimic the parent population or the population distribution the bigger my sample size gets. So that sample, that one single sample distribution, just is going to look like the population. A sampling distribution means that I take many, many, many samples of the same size from that population and then put all of the means of those samples on a graph. So particularly, I'm looking for the words sample mean in order for it to be a sampling distribution. Right? So a sampling distribution, as long as our sample size is big enough, will look roughly normal even if the population is not. But one single sample without taking the mean is not going to have that same effect. So I always like to say for this, make sure you're looking for the word mean. The magic is in the means. A distribution is not just going to suddenly turn normal just because we take a large sample. It's the process of taking the mean of many samples and putting all those means on a graph that makes it roughly normal. So again, on part B of that question, we'll go back to it. Because we just talked about one sample and not the mean, this is not actually a sampling distribution, and its shape is going to be similar to the shape of the original distribution, which was skewed to the right. So let's look at what the wording would be for a sampling distribution. So this one says, part C, if we wish to find the probability that a random sample of 35 students watched an average of less than 12 movies. So I'm talking about a sample mean of 12. Can we calculate this probability using the normal model? Yes, because now we're talking about a sample mean, And to calculate that probability, I would have to figure out what is the sampling distribution for the sample means of 35 students. So because we are talking about a sample mean, we can use the sampling distribution. And because our sample size is bigger than 30, we know that that sampling distribution will be roughly normal, even though our population was skewed to the right. So let's do that. Let's actually calculate that probability and figure that out. What is the probability that a random sample of 35 students watched an average of less than 12 movies? So going through our steps, the first step would be to check our assumptions and conditions to make sure that it is okay for us to use a normal model and to calculate this probability accurately. So we were given a random sample of 35 students. They told us that the sample was random. We can probably assume that 35 students is less than 10% of all students at the high school. That would mean there needs to be at least 350 students at the large high school, which is very reasonable. And then we're going to check to make sure that our sampling distribution is normal. Again, because our sample size is greater than 30, it's 35, we know our sampling distribution is roughly normal, even though the population is skewed to the right. So we know we're okay for the sampling distribution because our sample size is bigger than 30. So the second step would be to calculate the mean and standard deviation using our formulas from the formula chart. So the formula for mean says it's just going to be equal to the mean of the population, which they told us in the problem was 19.3. For the standard deviation of the sampling distribution, we take the original population standard deviation and divide by square root of n. So 15.8 divided by square root of 35, put that in the calculator, we get 2.67. So the mean is 19.3 movies, and the standard deviation is 2.67 movies. The next step is to use the normal model to calculate the probability, and that does include drawing a normal model. We are finding the probability that our sample mean would be less than 12. So there's my normal model. We found that the mean of that sampling distribution is 19.3. The standard deviation is 2.67. So again, I could go ahead and add and subtract 2.67 3 times on either side to get those markings. But I'm just going to go straight to the z-score. So z-score would be our observed value, which is 12. That's what we're trying to find the probability for, minus the mean of 19.3 divided by the standard deviation of our sampling distribution, which we calculated was 2.67. We get a z-score of negative 2.73. So that's about here, almost 3 standard deviations below the mean is where 12 ends up being. That's pretty far down. And then we want less than that, so we're going to shade less. Then we're going to go to our z-table, look up negative 2.73, find that probability. Because we are doing less than, and that's what our z-table gives us, we would just use that number, and we would get 0.0032. And then our last step, interpret the probability in context. There's about a 0.0032 probability that a sample of 35 students watched an average or mean of less than 12 movies. Right? So that is how we complete a sampling distributions problem for means. There's a lot of information in this video. We'll talk more about it in class next time and go over extra examples and any questions that you have. All right, see y'all next time. Talk to you later.